Earthquake prediction is one of the grand challenges in earth science. As a colleague of mine once said, if there's ever going to be a Nobel Prize given in geology, it will be to the person who figures out how to predict earthquakes.
Problems for a troubled
Earthquake.
Yep,
We're having an earthquake. Roll.
Earthquakes, of course, cause very strong ground shaking. That can cause landslides, liquefaction, building damage, can even cause deaths.
This is a very emotionally charged topic. People are jaded, they're tired of it, and they're suspicious about any publication that might claim they can predict earthquakes.
But we've never been able to predict anything about exactly when the earthquakes are going to occur or how big they're going to be.
But now with machine learning, all I can say is we're going to make dramatic advances that are going to surprise all of us. Five, 6 years ago, I was just really puzzled, of scratching my head about where are we going to go? There was no indication that we would see any kind of breakthrough regarding earthquake forecasting or really understanding how a fault worked between earthquakes.
When people talk about earthquake prediction, what they mean is predicting the time, location, and magnitude of a big earthquake, hopefully with enough skill and precision to be able to actually do something about it in advance. There's lots of things that seem like they might be useful ways to predict earthquakes. Planetary alignments, lunar phases, earth tides, animal behavior. But there's not turned out to be anything in those observations that tells us about future earthquakes.
Geophysical studies in Earth are challenging because the Earth is opaque, right? You can't see into it. And one of my colleagues said, well, why don't you apply artificial intelligence approaches to the seismic data in particular that you're looking at? And that was the beginning. This is acoustic data recorded on the earthquake machine at Chris Marone's lab at Penn State University. Chris Marone and I have known each other for quite a long time now, a deep thinker and one of the world's leading experts on earthquakes. So it took time to convince Chris what we're seeing was really real. And as he understood more and more about it, it became apparent to him that yes, this was the next major step we all had to take to include these tools into what we were doing.
Part of the advantage of working in this lab is that having espresso, coffee time. Chaz, you in?
Yeah, right here.
How we doing?
Good.
Get it set up where you want. So this is the earthquake machine. It is a servo-hydraulic biaxial deformation machine that's used for lots of kinds of experiments related to earthquake physics. There's two hydraulic cylinders. There's this one, and there's another hydraulic cylinder that's right here. In the experimental geometry, what happens is I'm going to push on both sides of this fault zone, and then I'm going to drive the center of it down under controlled conditions. You can hear the motion, and what you hear are the micro-earthquakes that are occurring during the frictional sliding that occurs in the earthquake. I think most people would ask the question of like, if we're going to study friction at the scale of the palm of my hands, how does that have anything to do with what happens on a real fault zone? But the parallels between what we see in the lab and what occurs on tectonic fault zones are just too close to ignore. To study earthquakes, one of the things that people do, and it's been done for a long time, is to capture the seismic energy that's radiated from a tectonic fault motion on Earth. There's so many little acoustic emissions that are occurring simultaneously that when you look at the record, you don't see an individual earthquake. You can't really make any sense out of it. And so people just ignored it for a long time. Machine learning changed all that. Machine learning sees inside the noise.
The first breakthrough finding was a signal that we had discarded as noise from the laboratory experiment and had just thrown away was rich with information about how the fault worked at all times. So we understand we can use 100% of the data instead of 5% of the data. That's the huge advance we have here because of this new toolbox. Secondly, using the same information could really nail down when the next earthquake would take place in the earthquake machine.
When they got to the point where they started to say to us, hey, we can predict when the events are going to occur, I was like, what? Really?
In practice, the way the algorithm is built is we measure the fault friction at all times. So we know the answer. So that's how we build the algorithm. So with the algorithm, we try to predict the answer. We compare it to the known truth. And once it's working really well, we say the model's working, then we go to data it's never seen. And very soon after that, they were able to predict when the next earthquake would take place in the earthquake machine. That was astonishing. So the question is, would this scale at all to Earth? We had no idea. You never have an earthquake, or you rarely have an earthquake that takes place on a human time scale. Most are 50 to 100 to 1,000 years apart. So what to do? It turns out that there's a certain kind of slip on faults in the Earth called slow slip. Slow slip is a slow earthquake. It takes place just as it sounds at a slow time scale. Instead of abruptly over seconds to minutes, it takes place over days to weeks to months. We had slow slip events beneath Vancouver Island, and that's why we went there for the next phase of the study. Bertrand and Claudia were leading the study, and they took the seismic data from Vancouver Island. Using those data sets, the machine learning model was built in the same manner it was in the laboratory. So they trained on 10 to 15 of these slow slip events, then applied it to the slow slip events that the model had never seen before. Incredibly, remarkably, we saw the same result. At any given time, the seismic signal had information telling you exactly what the displacement was at the Earth's surface. Moreover, you could predict when the next slip time took place. So what we learned in the laboratory, we were able to apply directly to the real Earth, and again, we were absolutely astonished. We're not forecasting earthquakes now, except in the laboratory. So what we're trying to do is advance earthquake science. That's really what we want to do. If we advance earthquake science, we'll advance the science of earthquake forecasting.
If anybody tells you that it will be impossible to ever predict earthquakes, well, that's a guess. If they tell you that they think that earthquakes are currently predictable in a useful way, well, they're wrong. But we may get there. We need to do it through the scientific process, carefully, rigorously. It's going to take time, it's going to take work, but the rewards are fantastic if it can ever happen.
And I think it's important for people to realize that we've basically just scratched the surface in terms of machine learning techniques. We've used the simplest machine learning techniques to predict lab earthquakes. There's probably a lot that can be learned by taking more sophisticated machine learning techniques. I don't think we'll be able to predict an earthquake in the next 5-10 years, but I do think we'll be able to ask, was there a precursor here that we could have seen?
This is a new set of tools that we have to embrace. The future really is using this to push forward new advances rapidly.